So how do I approximate the square root of 8? Yeah, so the square root of 8 would approximately be 1/4. No, I don't mean simplify it. Come on now. What's my approximation to the square root function near 4? This is, right here. That is what they're going to call in section 310, they're going to call this a linear approximation. They're going to use L of x. When they say linear approximation, what do I know they really mean? Tangent line. And we've done a shitload of those. So if I find the tangent line, that is the line that exactly meets it at that specific point and stays close to it around that point. And it's a line. So when they say linear approximation, that's just another name for tangent line. We're just going to use it more than we did before, but we know how the hell to find the damn thing. Now, this approximation, should it still be good or not so good? What I'm about to approximate, should it be good or not so good? Not so good. Why not so good? Because 8's pretty damn far away from 4. I don't care how nice your function is, right? So let's see what we get. 1/4 of 8 plus 1 is 3. And the square root of 8, if you do it, is 2.82 roughly. Now, of course, a lot of us might say that's pretty good, but that's pretty far off, right? 2.8 versus 3. Yes. So, was this really, really good? Was this approximation really good? Yes, it was really good. Why? I was really close to, where'd it go? I was close to what I built the approximation around. Where's the one place this approximation works perfectly? At 4. Why does it work perfectly at 4? Because another way to say that same question is, where does this tangent line agree with the function? At 4. Because that's the point it goes through, right? Okay, maybe. So we're repackaging stuff we've done before. So in this section, let me make this match up with what the book has. In this section it says, given f of x, the linear approximation to f of x is equal to f of a, and this is at, let me put some more words. Linear approximation at a is given by this. And if I don't explain it the way I just did, everybody thinks it's brand new and like, oh, more shit to know. No, this is tangent line. That's all it is. We're just calling it a linear approximation because that's what a tangent line does. Okay, I like it. I enjoy it. It's good. Okay, I like it. One other little thing in this section, oops, went the wrong way, is it becomes a huge idea later. So that's one thing is linear approximation. So that's a part of this section. There's one other kind of main idea that's given in 2 different ways in this section. So let me ask you, if I have some function and I change, so I'm somewhere on this function and I change x by a certain amount. So I change by delta x. Y is going to change by, the square root. Delta y. That's amazing stuff, right? Okay. So one way to look at this is, we use the same symbols they use. Yeah. So what is this right here? What is that point? What is that? I love you guys because you're like, I have no idea. But again, here's f of x. So using the symbols I've got, what is this? No. This point right there, the input is x. So what's the output? F of x. I love you guys. Trick question? Not really, but a weird question, yeah. It's freaking f of x, right? And what's this one here? F of x plus delta x. I like it. So what is delta y then? What is delta y? What is it equal to? It's the difference in the heights, right? So it's going to be this minus this. All right, there's one thing right there. This is what we call, I've called it this before, a gross step. Not meaning you took a step and stepped in something you'd rather not, but gross meaning big, right? This symbol means bigger than infinitesimally small. So this could be a step of 0.00007, which is still huge compared to dy. What's dy mean? Infinitesimally small, like insanely. Think of something as small. Now think of something 1/1,000th, and then keep going forever. 1/1,000th the sign of that. The 1/1,000th of dy is crazy. Is that pretty cool? Does that look at all familiar? Is that look at all familiar? If I replace delta x with h, like we've used before, doesn't it look crazy familiar, right? What is it? It's the... Yes, cool. It's the top of the limit formula for derivative, right? Stay with me now, stay with me. So, to get to dy, what I do is, if I... see if you guys are cool. What is dy dx? If y is f of x, what is dy dx? It's kind of a silly question. It's f prime, right? So then what's dy? Multiply dx up. Let me show you real quick. I wanted to do it that way first, just because we know what dy dx is in terms of prime. There you go. So this is not really saying anything explosive. But how do we get from here to there? Well, if I divide both of these by delta x, and then take a limit as delta x goes to 0, this will be dy dx, right? And what's this? The limit as delta x goes to 0, this is f prime. And then I become that. So this is how you go from a gross step, a huge delta x, and what's huge mean? 0.00007, that's huge, to a infinitesimal step in x. Okay. So these are just going to be two little formulas you're going to use for a problem like... no, that's too basic. Here. The radius of a sphere. Let's do this problem. The radius of a sphere was measured and found to be 21 centimeters with the possible error of at most 0.05. So the error in the radius is 0.05 centimeters. What is the maximum error in the volume of the sphere? So what's the volume formula for sphere? It's like saying Favre. Brett Favre and his sphere. Yes. Sweet. So what's dv dt? dt, get out of there, dt. dr. This is kind of nice. What happens? 3 comes down. 4 pi r squared. Why is there nothing after this? Because it would be dr, which is 1, right? So then the uncertainty in the volume, the error in the volume would equal 4 pi r squared times the error in the radius. And now I just throw shit in. So the error in the volume would equal this times the error in the radius. So now I know the error in the radius, I know the radius, I can get the error in the volume. Okay, so that's the other part of this section. This kind of idea though, this right here, going from here to here, just to kind of, This is called the differential. It's a little different from stuff we've done before, but it's going to become huge when we start doing anti-differentiation. I might as well talk about it right now. So if I have y equals x cubed, then I can immediately do dy equals 3x squared dx. Same idea as just, it would be down here, and then I just throw it up there, right? If I had u equals sine t, du equals cosine t dt. So it's just, instead of putting du over dt, we multiply the dt up. Ooh, right? But when we get to anti-differentiation, also known as integrals, this will be huge. Huge. All right. So 310, there's really not much in it. In fact, most of it is old stuff repackaged. Tangent lines. Okay. Now, can somebody remind me, by the way, just so you know, just so you have something to look forward to, we're going to get at about 9. I got to leave a little early to do an evaluation. Something to look forward to as you try to make it through this. Can somebody tell me, what are trig functions based off of? Most fundamentally, even before triangles. What do we base trig functions off of? Unit circle. Right? Now, we're going to talk about section 311. You're going to have to do the homework in section 311. I'm not going to make you memorize any of the formulas from 311. But if I don't have you do 311 now, you're going to die later in your math career. You got to know what these things are. So normal trig functions like sine and cosine and etc. are based on the unit circle. Right? You guys with me? So, there's some really cool shit out there about what if I used a unit square instead? What kind of trig functions would that lead to? You can actually see some really cool animations if you search unit square trigonometry. Curious how many of you guys would even do that. This isn't that. This is saying, what if instead of a circle I used a hyperbola? So these are going to lead to hyperbolic trig functions. Wow. Now, one level of this is, what does it mean geometrically? That's the part that's less important for working, but more important for conceptually and to like go, whoa, that's some cool shit. So see how the unit circle has that equation. So if I say unit hyperbola, that sounds weird, but what's the main difference between an ellipse, which a circle is a special one of, and a hyperbola? Uh-oh. So circle equation has a plus. To make it a hyperbola, I just make it a minus. You guys remember that? I love, if I say add two positive numbers. Now think about this. Just, all right, I'm going to have to do this. If I said, give me two positive numbers to add to be 8, are you limited in the size of those numbers? Give me two positive numbers to add to be 8. 6 and 2. Or let me say it like this, non-negative. So it could be 8 and 0, right? 0 and 8. Right? 6 and 2, 4 and 4. Ooh. If I say give me two positive numbers whose difference is 8, is there a limit on how big you make either one of them? No. Do you understand what I'm trying to say? Since there's a plus in a circle equation, it's contained. There's a limit in how far you can go. There's a minus on a hyperbola equation. It's uncontained. You can go insane if one is 108, the other one's 100. One is 1,000,000,008, the other one's 1,000,000,000. But for a circle, they're both supposed to be positive because we've got squares in the damn thing. It's contained. You can only go so far. Is that? I love that idea. Very infrequently is it looked like that. So here we base everything off of this guy. And to be honest, well, I don't know. I don't want to get too much into the history of this. So I'm going to call, I can't use cosine because it already means unit circle. So hyperbolic, instead we use cosh. Oh, baby. Let me just use t so I don't get all freaky. Cosh t and sinh t. Let me use, oh, freak it. Just use x. Just know that this is kind of behind the scenes. Now here's the other, so one side is the geometrical aspect of it. It's really kind of cool. The other side, I didn't even have to talk about any of what I just did for you to be able to do problems, because there is another side to these, which is just what are their definitions. So cosh, I always forget it is plus or minus. No. Cosh is the one that's e to the x plus e to the negative x over 2. Sinh is the one that's e to the x minus e to the negative x over 2. So I could have started my discussion with, there are multiple places in engineering and physics and other kind of math areas where these kind of expressions show up. So this is just a way to consolidate that shit. But it's kind of beautiful that that leads to this, which actually you can look at purely geometrically. It's really nifty. So what is, for example, what's cosh of 0? Yeah, what's e to the 0? 1 plus e to the 0. 1 is 2 divided by 2 is 1. And what's sinh of 0? Now it's going to be 1 minus 1 over 2. 0. So watch this real quick. That's the computational side of things. If I look at what's happening on a graph, here, let me just focus on one piece of this hyperbola. So here's what, oh my God, and a half. Oh, it's not going to come out beautiful, Jeff, so don't worry about it. So here's one side of this hyperbola, right? My scale's all freaky out here. Sinh, so if I am at 0 degrees, sort of, cosh is going to be this length. Sinh is going to be, like if I'm here instead, sinh would be that y piece. It's still sinh means y, cosh means x. So if I'm at this point, this will be sinh of whatever that is, and this will be cosh of whatever that is. That's kind of nifty. I mean, that's, so here we just looked at 0 degrees. That means that cosh is 1 and sinh is 0 because it's not, the y doesn't exist yet. So if I do different degrees, I can see what the y piece is and what the x piece would be. That's really, 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 really freaky cool. Yes?
So it's the same answer if you're thinking of it on the graph too, right? In trig, cosine 0 is 1 and sine 0 is 0.
But notice what's going to happen to cosine for bigger values. Doesn't the output go from 1 and go up?
That's what I was asking.
Yeah.
Like,
so that's why
you
it's
have
not.
to use the formula.
It's not the same. So here, what was the biggest cosh could be, and what was the biggest sinh could be? They live between 1 and negative 1, right? Because it's plus. They have to live between. This is minus, so now they can go as big as they want to get. Negative, positive. Yes?
And why again did you say this was helpful for real-world engineering?
This is so for example, this is the most basic example there is. But if you've ever noticed telephone pole, and they still exist out there, eventually they all get on the ground or something, but when you have the wire hanging in between, is it ever just straight across? Physically, it can't be. It's going to always make this shape called a catenary. And that exact curve is only described by that function. Or let me say it like this. most easily described by that function. You can make a combination of e shit, or you just say cosh of something and be done with it. So these exist geometrically. Can't argue with it. If I look at a hyperbola instead of a circle, they exist geometrically. As a computational thing, it makes a lot of work here compacted, right? And you actually have hyperbolic capability on your calculators. Not on your face of the calculator, I don't think, but it's under the math button somewhere. Okay. So there's going to be questions in here about the derivatives. How would you do the derivative of cosh? What would you do? You would just take the derivative of what cosh is. You know the derivatives of all these pieces, don't you? So you can figure out what the derivative of cosh is. And if you look at it very quickly, what's the derivative of e to the x? What's the derivative of e negative x? Negative e negative. Isn't that this? Isn't the derivative of cosh and sine? Cosh and sinh. Now what's weird is the derivative of sinh is cosh. There's no negative in there. So that's why I don't make you memorize those, because then it really, really messes with your brain. And we should expect not everything's going to be perfect, but there's so many identities that, in fact, what's one identity you can see here? Cosh squared minus sinh squared is 1, which is related to cosh squared plus sine squared is 1. All right. Okay, I like it. So 311, you need to know what they are. You need to know what they're based on. You need to work and play around with them a little bit. Right, but I'm not going to make you memorize the definitions. I'm not going to make you memorize the derivatives. They're all right there in the section for you to do. I like it. I want you to know they exist, how they interact with each other. There's a few problems, like there's a catenary problem in there and so forth. Is there the St. Louis arch problem? No? Too bad. Okay. All right. Man, today's chocolate block full. So last thing for today. Okay. So, real quick word about it. If you see exponentials involved in things you got to take derivatives of, you should say, oh, thank favorite deity, whatever you like the best. Thank God, thank Buddha, thank the god of coffee, thank whatever. Right? Because e to the x is like, sweet. While I'm talking about e to the x, what's the derivative of e to the ax? E to the ax. What's its derivative? Yeah, a e to the x. What's it look like happens? Just say it. What's it look like happens? Looks like the a comes down, but does this change? No, because what's the fundamental idea behind derivatives and exponentials? It stays the same. So where's that a really come from? What rule? Chain rule. So what's the derivative of this? You don't put 2e to the 2x squared. That's not thinking. What's the derivative of e to anything? E to that thing. And they have to multiply by the derivative of the inside. What's the derivative of 2x squared? There. Okay. So it is chain rule. It is not some version of power rule. It just, for linear functions, it kind of looks like it. Don't be doing this weird shit. No. It's not x to a power, so it can't have that rule. I like it. So, what we're getting into now, chapter 4. Oh my God. And real quick, I know it feels like we've done a lot. 3.7, not that big of a step from what we've done before it. 3.10, not making you memorize any of it. You just have to be able to use the functions they give you in this section. That's really it for 3.10. I'm sorry, 3.11. 3.10 was the linear approximation, which was just tangent lines. Right? So all this stuff is kind of like repackaged earlier stuff we've done. Now, of course, if you didn't understand it before, here it is again. Shit. Time to really understand it. This, for one, is actually stuff we've done before too. Because I was getting you ready for this. So help me out. At what values of x could f of x have maxes or mins? Let's think about this. Where could they happen? And now that we know calculus, we can answer this better. If it's just a parabola, we could do that in pre-calculus. The minute it's more than just a parabola, we need calculus, right? So come up with a picture. Draw a picture that's got a max and a min on it somehow. In fact, let me be more specific. See if you guys agree. Local max, local min. Just figure out what the hell that means. So I'm going to draw one. Let me see if it matches up with what you guys are drawing. All right, that's one that's got a bunch, right? If I wanted to, let me see. Make a big point here. Okay, now watch. Is this a local max or a local min? No. Is it a local max or a local min? What does local mean? Think about delta. It means not very far away from the point I'm considering. So within a little neighborhood, is that a max or a min? So this is what local means. It can't be a minimum because it's not the location of a valley, is it? Isn't that the location of a hill? That hill happens to be the smallest hill around there, but it's still a hill. Shit, poor little dude. Do you guys, even though that local max is smaller than this is still a local minimum. Yeah. So that word local is related to the idea of delta, which means close to the thing I'm looking at. So this is like a profit function. I wish I could get out here, but normally what happens is, in reality, this is where I live. These are the only accessible things. So then I want to be there. I'm like, ooh, if we got over there, we have unlimited. Well, the reason that's unlimited is it's physically impossible. The equation says, yeah, but reality says, nope. So I want to know my local maxes, because maybe it's even like this, and I'm like, oh, I can't even get there, shit. Which means, would that be the best place to be? In this case, no, right there's the best place to be. Right? That's the most profit you can make. I like it. So these are local mins. Everywhere you see a dip like that, everywhere you see a valley, those are mins. That hopefully just makes sense. Everywhere you see a mountain, a little hill, that's a max, right? So this is a local max, this is a local min, this is a local max. Okay. What time is it? Okay. Now, right here, if this is where I lived, if this is the only things that are accessible to me, is this even a little higher? No, it's about the same height, so these are like the same height. Those would be absolute max. That's the biggest it gets in the allowable interval. Why is it not a local max? Because if you look at the whole function, no, it's not a peak, it's not a valley, it's not a local max or a min. Okay, maybe. So where do local maxes and means? What are local maxes and mins seen to happen related to a calculus idea? We already kind of talked about this, yeah. Where there's a horizontal tangent line. There's one other place they could occur. Let me draw a little bit different function, one that's not as nice. This is a nice polynomial function. I call it the Loch Ness Monster function. Does this have a local max or a min? This is weird to draw. Does it have a local max? Say yes, because there is a point where it gets the biggest in that area, right? Does it have a local min? Yes, because there's a point where it gets the smallest in that area. Are those horizontal tangent line locations? Is it differentiable there? That's where the derivative is undefined. So where could they be? At what values of x could, this is a key word that I try to raise, could this have local max or min at places where f prime of x is 0 or f prime of x undefined? If I find a place where f prime of x is 0, is that definitely a max or a min? There's a really easy function we looked at earlier that has a place where its horizontal tangent line goes to 0, but keeps going, x cubed. Here's my fifth puberty. Right? There's a place where it has a horizontal tangent line. The derivative is 0 at 0 for x cubed. We saw that earlier, but it keeps going up. That's why could. So if I find all the places, now here's what I really want you with me. If I find all the places where these two things are true, those are the places where it could have a local max or min. So those places are special. So we're going to call them frickin' critical points. So if I say find the critical points for this function, that just means where's the derivative 0 or where's the derivative undefined. And I've been getting you ready for this.
You're calling critical points for f is 0 or undefined, but they're not necessarily the classes.
Beautiful. That's why I don't call them max or min. I call